So the main idea of Euler's method is that you've got some differential equation, specifically some first order differential equation of the form dy dt equals, let's say, some function of t and y. And maybe it's not something you can solve directly, or maybe it would be too tedious to solve it. But let's say we don't really need an exact solution in the form of y equals some function of t. Let's say we just need an approximation, and specifically a numerical approximation. Let's say we just want to know, like, when t is 5, what's the y value? So what we can do here, given an initial condition, let's say our initial condition is y of t naught is y naught. That is, when t equals some initial value called t sub 0, y equals some initial value called y sub 0. The idea is, if we're looking at that initial condition, like let's say we have a direction field here. And we have our initial condition, t naught, y naught. The whole point of a differential equation is that it tells you at any ty coordinates, what's the slope going to be. So let's say you calculate that slope, and you find that it's got some slope at that point. What we're essentially doing here is we're looking at the direction field, but only at that one point. We don't care about all the rest of the points, just the one point of the initial conditions. If we imagine that the solution curve is almost linear, we can say, suppose this goes in a straight line for a little distance to some new location. Let's call that location T1, Y1. That's now another point, Ty coordinates. So we could plug that back into the original differential equation and find the new slope at that location. And let's say we calculated a new slope. Let's say this is the new slope. We can now follow that slope as if the curve was a straight line a little bit further till we get to some other location. Let's call that T2, Y2. And let's say at that location, we recalculate the slope, plug in T2 and Y2 into the original differential equation, get a slope. And let's say that looks like this. We follow that line some distance, get to a new location, which we'll call T3, Y3. Plug those into the original differential equation, recalculate the slope, and then follow that for a short distance to get a new location, T4, Y4, and so on. So the idea is we're going through this sequence of tiny linear approximations. And of course, the solution itself is probably not linear. The actual solution probably is going to look something like this. So this connect the dots series is probably not going to be all that accurate to the actual function. But for at least a little while, it's going to be a fairly accurate approximation. And then the further you get from the original point, the less accurate it becomes. Any questions on that so far? Just the general idea of Euler's method. So if we're going through this sequence of approximations, calculate the slope, go a little distance in that direction, recalculate the slope, go a little distance in that direction, recalculate the slope, and so on. To keep track of this, I usually find it's useful to make a data table, to set up a data table with a column for t, a column for y, and also a column for the slope, because we want to know what's the slope at each of those points. So let's say we make a data table with columns for t, y, y prime, because we want to know the slope at each of these locations. And also we want to keep track of how far are we going in the t direction and how far are we going in the y direction. So let's call these columns delta t and delta y. So what we're going to do, we're going to start with the initial conditions. Use the differential equation itself to calculate the slope. Use the slope to figure out how far we're going in the t and y directions. and then add those to the original t and y coordinates to figure out the new t and y coordinates. Any questions on that general outline so far?
I have a question. How would we determine the change of t and the change of y if we are only given a slope? Are we supposed to just give a small value to one of them and then see what the other results in, or?
Yeah, exactly. Because if you go back to the idea of what slope is, if you've got some curve, like let's say this curve is the actual solution. And let's say we have a point on that curve. So let's say this point is T1, Y1. And we want to get to another point on that curve, T2, Y2. What we're doing is we're approximating this based on the slope. The slope at this point, the derivative is the function or the value y prime. So let's say we continue this some distance. Is this tangent line actually going to hit the other point on the curve?
No, it's not.
Right, it's probably going to miss, unless the curve happens to curve in a certain way or happens to be a straight line. But the tangent line gets us at least an approximation. So if we take a look at the amount we're going in the t direction and the amount we're going in the y direction, the derivative at least tells us the ratio of those. Let's say we call this distance delta t. And you're right, we basically just choose a small arbitrary value for that, usually called h, as in the horizontal step. And formally, you don't need to use the same h, the same horizontal step for each delta t, but it's useful if you just for consistency, it's usually a good idea to use the same value for each step. So delta t is just going to be the same tiny distance or tiny amount of time each step. And we usually call that h for horizontal step. And then this value, notice that this is not truly delta y. Delta y would be this value up to the actual point. But we can use this other value as a close approximation for delta y. So what we can say is the derivative dy dt, so dy dt is the slope of the tangent line. That's approximately equal to the ratio of the actual change in y versus the actual change in t. Any questions on the distinction between those so far? The slope of the tangent line versus the ratio of the actual change in y and the actual change in t.
No, I understand. Thank you.
Okay. So let's say we know the slope of the tangent line, because if we know t and y, we can calculate the derivative. So we know dy dt. And let's say delta h is just some tiny value that we've chosen. How would you solve for delta y?
You would just plug in the delta t and then multiply that on both sides and just solve for delta y.
Exactly. So we can say delta y is approximately the derivative at that point times delta t. So that's how we're going to find delta y. Delta y is the derivative times the time step. And then once we've chosen our delta t, which is just our tiny h step, and we've calculated delta y by multiplying y prime times delta t, then we can add delta t to the original t to get the next t value, and add delta y to the original y to get the next y value. And then repeat the whole process as many times as we need to get to a certain ty coordinate. Any questions on the theory behind that so far before we try out an example? So let's throw in some actual equations here and some numbers. Let's say our differential equation is y prime equals let's say t squared minus y squared. Nonlinear, non-separable might be kind of tricky to solve analytically. But we can use Euler's method to get an approximation, a connect the dots approximation of the solution curve. And of course, we'll need an initial condition also. Let's say our initial condition is y of 0 equals 2. So we'll use that for our t naught and y naught values. So t naught is 0, y naught is 2. We can immediately use those to calculate the derivative. If you plug in 0 for t and 2 for y, what do you get for the derivative there?
You get -4.
Yeah. And then delta t, we're just going to have to choose a h step. We'll choose some constant distance or some constant amount of time that'll be our consistent h step. Let's say for now we use the h step of, let's say just 1. So each step we're going 1 forward in time and some amount up or down in y value. To find delta y, we can just multiply y prime times delta t. Because again, y prime is approximately change in y over change in t. So change in y is approximately y prime times delta t. In other words, y prime times h. So we just multiply those, -4 times 1, we get -4. So that means starting from 0, 2, we can go forward 1 in the t direction and down 4 in the negative y direction. And that means we can just add those to the original ty coordinates. Original t value plus delta t is the new t value. Original y value plus delta y is our new y value. Any questions on that so far? So 1, -2 is the next point we're looking at. That won't truly be a point on the solution curve, but it'll at least be fairly close to it. And then we recalculate y prime. Plug in 1 for t and -2 for y, and what do we get here?
-3.
Yeah, so that means the new slope is -3. And our delta t, we're still going to use the same delta t step. In fact, this is just always going to be the same delta t step. And then for delta y, again, we can just multiply y prime times that delta t. -3 times 1 is -3. So that means our next step, our next transition to the next data point is going to be 1 forward in the t direction and -3 down in the negative y direction. So original t value 1 plus 1 more is now 2. Original y value -2 plus -3 is now -5. So that's our new data point, 2, -5. And then we fill those in, 2 for t, -5 for y, and what do we get for y prime?
-21.
So that will be our new slope. And then again, we can multiply y prime times delta t, -21 times 1 to get our new delta y, how far we're going in the y direction. Add delta t to get our new t value. Add delta y to original y to get our new y value. So 3, -26 will be the next data point on the graph. And continue this process. Plug these into here, 3 squared minus 26 squared. That'll give you your new y prime and keep going until you get to, usually what we care about is like when t is 5, what's y going to be? Or when t is a certain value, what's y going to be? So keep this going until you get to the required t value, and this will tell you approximately what y will be at that point. And you can even graph this. You can now, once you got this, you can just take the t column and the y column and just graph that as a scatter plot. 0, 2, 1, -2, 2, -5, and so on. Plot those as points on the graph and connect them with a smooth curve, and that at least gives you an approximation for the solution. So that's the core idea of Euler's method, making this dot-to-dot approximation of the true solution. Any questions on that so far?
Yeah, kind of not really related, but does that mean the actual curve itself subtract like the approximation gives like a residual. Is that like the truncation error?
Yeah, we could call that the error term. That the difference between the actual solution versus this approximation would be the error.
Okay.
And with this example, the way we've just done it, the error is going to be pretty big. I would expect these values to be way off from the actual solution. How do you think we could make this more accurate? What change could we make to this process?
Decrease the delta t.
Yeah, if we use a smaller delta t, the smaller we make delta t, the more steps it's going to take, but the more accurate it will be. So for instance, let's say we tried the same process, but let's say we made delta t, let's say 1/2 instead. In that case, y prime times delta t would be -2 instead. So from 0, we're going 0.5 forward. From 2, we're going 2 downwards. Now we plug these in, 0.5 squared plus or minus 0 squared would be positive 0.25. And then delta t is still going to be the same 0.5. 0.25 times 0.5 would be 1/8 or 0.125. So that means that's our new delta t and delta y. And notice that even already we're just changing it from delta t equals 1 to delta t equals 1/2. We're already getting a little more detail. We're getting the fact that the curve goes up a little bit at this point. In the previous one, we were thinking, well, it's going to go down the whole time. This one gets us a little bit where it seems to be going up. So that might be more accurate, or it might be shying away from accuracy. Maybe the accurate version is always decreasing. But the smaller you make the delta t step, the more accurate it becomes overall. And we could keep this going, add this delta t to the original t value to get 1, add this delta y to the previous y value to get the new y value, 0.125, plug those in to the original differential equation to get a new y prime, and so on. And of course, since we made the delta t half of what it was, this is going to take twice as many steps to get to a certain t value. So it takes more effort, more time to make it happen, but it gets you more accuracy. Or if we wanted even more accuracy, let's say we make delta t 1/100th. That's going to take 100 times as many steps, but it's going to end up being much, much more accurate. Any questions on that so far? Of course, there's a better way to do this also. I mean, I would certainly recommend trying this out by hand at least a few times to get a feel for it. But if you're ultimately just doing the same calculation over and over and over and over and over again, what's an ideal tool for doing the same calculation over and over again?
A computer?
Yeah, we can computerize this and say, let's make this do steps of delta t equals 1/100th of a step. And it'll take hundreds of steps, but a computer can do that in a blink of an eye. So you can get a lot of accuracy really fast once you've done the initial effort of setting it up in the first place. And specifically, what kind of computer program works really well with columns of numbers like this?
Excel.
Sorry, what was that?
I say Excel.
Yeah, Excel or any other spreadsheet program. Essentially, what we're doing is a spreadsheet by hand. We may as well just turn that into a spreadsheet on the computer. So let's try that out. Let me pull up a spreadsheet here. I've got OpenOffice here just because that's what I'm accustomed to, but you can use any spreadsheet program and it should work fine. So let's say we set up our T column and our Y column and our Y prime column, our delta T column and our delta Y column. And we'll want to put in our initial conditions manually. So our initial conditions were 0 and 2. And for Y prime, we want to set Y prime equal to T squared minus Y squared. And I can do that just by setting up a formula. If I just type equals to tell the spreadsheet program I want to write a formula, then I just click on this cell, the T value squared, minus click on the Y value squared. So that's the T value squared minus the Y value squared. And that gives us exactly what it should be. So that's the y prime, the slope at that point. And then for delta t, let's say we're using that 1/2 value. Actually, let me put this off to the side. Let's just say our h value is 0.5. If I put it elsewhere and refer to it, then I can change that later. So equals that value. Also, I don't want this to change, so I'm going to put some dollar signs here. Have you seen what the dollar signs mean in that context?
It will just keep it constant.
Yeah, if I move the formulas around, I don't want it to update this formula. I want to keep it as cell H2 no matter what. So for instance, if I take this cell, which refers to values B2 and C2, and drag it down, this cell is now referring to cells B3 and C3 instead of B2 and C2. It auto updates. But if I take this one and drag it down, it's still referring to H2 because I put in the dollar sign to say, keep column H, keep row 2, don't change those if I move this formula around. And then delta y, I want to multiply y prime times delta t. And I can drag that down as well. Problem is I can't just drag down the 0 and 2 because those were manually inputted. How do I calculate the new t value and the new y value?
You add the delta t to the previous t.
Yeah, the previous t value plus delta t. And likewise for y, I take the previous y value plus delta y. And notice that it auto updates everything else. In fact, now that I've got this second row written entirely in terms of formulas, everything here is written in terms of formulas referring to other cells. And the only one I need to make sure it doesn't update is H2, which represents the time step. What I can now do is just select this entire row that's all formulas and drag it down. Like, let's say I want to find what's the value of y when t is 5. I just drag this down until I get to, don't even need to go that far, just to t equals 5. And now this suggests when t is 5, y is about 0.32. I could even graph this by selecting these two columns and saying data, no, where was it? Table, there it is, table. We want an XY scatter plot. So that gives us the suggested solution curve. And of course, this is probably wildly inaccurate. We can get more accuracy by doing what?
Changing the delta t to a smaller value.
And setting it up like this makes that very easy. I just change this one number, let's say to 0.1, and it automatically updates everything that was referring to that. Of course, I'll now have to drag this down much further to get to the same t equals 5 final point. And note that this gives us a very different result. Previously, we were getting when t is 5, y is about 0.3 something. Now this is saying when t is 5, y is 4.89. And I would expect that's probably a lot more accurate because smaller delta t suggests more accuracy. So this line, this curve suggests much more accurately what that curve is probably like in terms of the shape of the graph. Any questions on that so far? And again, if we want even more accuracy, we could just make this even smaller. Let's say we make the t step 0.01. And then of course, we'll have to drag this down much further if we wanted to get to t equals 5. Well, let's try that. Drag that down a few hundred rows. Something like that. And note that this is not actually very much change in accuracy. The t, when we were using h equals 0.1, we got when t is 5, y is about 4.89. We're still getting, even with 10 times more calculations, when t is 5, y is about 4.9. So it looks like the h equals 0.1 was actually a very good choice there in terms of a compromise between pretty darn good accuracy, but not hundreds of calculations. But just out of the sake of curiosity, let's try graphing these columns, see what it looks like. Graph that as a XY scatter plot. And that looks like almost identical to what we had for the h equals 0.1. And of course, the further out you go, like let's say we wanted to get from t equals 0 to t equals 50. In that case, since that's so far away from the initial conditions, I would expect that the approximation would diverge even worse. Typically, the further you get from the initial conditions, the less accurate it becomes. But you can compensate for that by using a smaller and smaller h step, with the cost, of course, that the smaller your h step is, the more calculations are required. But again, with a computer program like a spreadsheet or code or whatever you want to set up, you can have that done really quickly. Just tell the computer what you want to do, as long as you're giving very precise instructions, and then wait for it to make the calculations and you're done. So that's Euler's method, using this sequence of approximations to get, if you take enough time or use a computer, a remarkably close approximation to the actual solution. Any questions on how that works? Or are there any other examples or topics you'd like to work on?
Could you briefly go over Picard's iterations? Because from what I understand, is it similar to your Euler's concept?
In some ways, yeah. I mean, Euler's method and Picard's method are both ways of turning an initial value problem you can't necessarily solve into a sequential approximation. So you can at least get an approximation of the solution. The big difference is Euler's method uses derivatives to go one step at a time and get a sequence of numerical points. Whereas Picard's method uses integrals to get not a sequence of points, but a sequence of functions that are closer and closer approximations. So let's take a look at that idea of Picard's method. One other difference is Picard's method is set up to assume that the initial value is 0, 0. If the initial value is not 0, 0, you can always just modify your coordinate system so that it is. Like for instance, let's say your coordinate system has this as your initial condition. Let's say, I don't know, 4 or 5. What you can do is set up a new coordinate system. Like let's say these are your x and y axes. If you set up a new coordinate system with a u axis and a v axis, the new coordinates at that point are now 0, 0. And then you need to make some modern modifications, like for instance, u is equal to x minus 4 and y is equal to v, or v is equal to y minus 5. Because v needs to be the y value 5 modified to become 0, and u needs to be the x value 4 modified to become 0. So to make this coordinate system shift, you would just take every x and replace it with u plus 4, if you solve this for x, and replace every y with v plus 5. Rewrite your original differential equation, but replace every u with x, or you replace every x with u plus 4, replace every y with v plus 5. But since it's just y equals 1v plus 5 and x equals 1u plus 4, it turns out that dy dx is going to be the same as dv du. So you don't need to change the derivative, just a few coordinate shifts within the equation itself.
I see.
So in general, no matter what your initial condition is, it's in terms of the original, let's say, x and y variables, it's always possible to set up a new coordinate system so that your initial condition is now called 0, 0. And that's a good starting point to standardize Picard's method.
That makes a lot more sense.
I mean, that's the main idea, the coordinate system shift. In practice, you often just start with, let's assume the initial condition is 0, 0. But if it's not, you need to make this coordinate system shift first. Basically just to standardize the inputs. So once you've standardized it to 0, 0 as your initial conditions, then you can use the same procedure every time. And that's basically to eliminate an extra plus some constant in each step. Because when you integrate, you get plus a constant. But if you're assuming the initial condition is 0, 0, then your plus a constant becomes 0. So it's much easier to work with. Any other questions on the coordinate transform first, before we take a look at the actual approximation method? Okay, so for Picard's method, the idea is we assume we've got some differential equation, some initial value problem with the differential equation dy dx equals some function of x and y. And also the initial condition that's specifically at the origin, x equals 0, y equals 0. And again, if the initial condition is anywhere else, you just use a coordinate transform to create this new coordinate system so that it is called 0, 0. The idea is Picard's method starts with making a guess. And the default guess is we're going to guess that the solution is y equals 0. And of course, that's probably not actually a solution. It might be, maybe y equals 0 is an equilibrium solution, but let's say presumably it is not actually the solution. That means when you plug it in, it makes this differential equation not true. What we're going to do is we're going to make a modification that makes it still not true, but at least a closer approximation. And this approximation involves rewriting the differential equation as an integral equation. Specifically, if you take the integral of both sides, what does the left side become?
Just y.
Yeah, just y. So y should equal the integral of all this stuff with respect to x. So if y truly is a solution, then when you take that function of x and y, whatever the other side of the equation is, and integrate with respect to x, the result should just be y itself. If the result is not y itself, then that means y is not a solution. But the bonus here is when you apply this integral, if y is not a solution, the result is another function, a different function that ideally should be closer to the actual solution. A more complicated function that more closely matches the actual solution curve. So we're going to take our original guess, 0, plug it in here. So we'll take whatever this function is. And the capital F here just means the other side of the differential equation, basically. But instead of writing in y as some arbitrary variable, we're going to replace y with 0. That gets us a function of just x that we can integrate. And that gives us a new, more complicated function for y. Let's call that y1. And that'll be a more accurate approximation than just a flat line, but still not very accurate. So what we're going to do is we're going to take that y1 and plug that into the original again and integrate again. And again, if y1 was truly a solution, this shouldn't change it. We should just get another copy of y1. But presumably y1 is not a solution, so we get a different function, which we're going to call y2. And ideally, that should be a closer approximation of the actual solution. Then plug that in as our new guess and integrate again to get a more refined guess. So this is what's called an iterative method or a recursive method. It keeps looping back on itself to turn our guess into a better guess, into a better guess, into a better guess, eventually approaching the actual solution. And of course, it'll never, in most cases, it'll never get there. You get an infinite sequence of polynomials usually that gets closer and closer to the actual solution. And ideally, that sequence of polynomials approaches some sort of Taylor series polynomial, which you might recognize as the solution of the Taylor series of a specific function. Maybe it looks like the Taylor series of e to the 5x, or maybe the Taylor series of sine of 3x or something like that. So let's try a quick example. Let's say our differential equation is dy dx equals, let's say, three xy. And of course, this one is separable. We could solve it by separation of variables. It's also linear, so we could solve it by integrating factors. But let's try using the Picard's method formula, Picard's method of iterated integrals to solve this. Again, we're going to start by guessing that y equals 0. And let's call that y sub 0 of x. Of course, if you plug in 0, wait, does that work? That's a solution, isn't it? Derivative of 0, 0, 0 equals 3x times 0. So this is not actually a good example. Let's say we're using the example 3xy plus 1. That way 0 is not really a solution. So filling that into our integral, the idea of integrating this whole thing with that y value. So I'm just going to write out this entire side of the equation. This is the f of xy we're talking about. Write out that whole thing integrated with respect to x. But instead of y, I'm going to use our previous guess. And we'll call that y1. So integral, this is just going to be 0 plus 1. What's the integral of 1 dx?
X.
Yeah. So our first order approximation is y1 equals x. And of course, that's not a solution either. You plug in x here, you get 3x squared plus 1, which is not the same as the derivative of x at all. But we can use that as our guess, our starting point for the next step. Next step is we're going to write out that same 3xy plus 1, that same function from our original differential equation, integrating it. But we're going to replace y with our previous best guess. This becomes our new guess. So we now have 3x times x plus 1, 3x squared plus 1. And what do we get if we integrate that?
3x cubed over 3 plus x.
Yeah. And the 3's cancel out, so we just get x cubed plus x. So that's going to be our next guess, y2. And by the way, when we integrate, formally, we should have a plus c here. But how do you usually find the plus c for a specific solution?
You set it to initial condition.
Yeah,
So
and if we fill in these initial conditions, x is 0, y is 0, do we need anything else added here?
Nope.
No, the plus c is just going to be 0. This is really the main reason why we standardize this by treating the initial conditions as 0, 0, or using a modified coordinate system if we need to. That way, we don't need to worry about a plus c. The plus c will always be 0 because our initial conditions are 0, 0. So that's our y2. That should be at least closer to a solution to this, even though it's not truly a solution. And then we're going to go through the same process again. Once more, we're going to write out integral of this whole thing integrated with respect to x. But now we're going to replace y with our previous best guess. So y is going to be replaced with x cubed plus x. And of course, we'll want to distribute that. So we get 3x times x cubed is 3x to the 4th. 3x times x is 3x squared. And then we also have plus 1. Integrate that with respect to x, and what do you get?
3/5 x to the 5th plus x cubed plus x.
Yeah. And so that's what we'll call y3. And notice that that's the same as we had before plus one extra term. Just like this was the same as we had before plus one extra term. In fact, as we integrate this, because it's this nice neat polynomial, each time we integrate, we're just going to get the same as we had before plus one extra term. So once you've established that pattern, you can ignore what we had before and just focus on what's the new extra term we get at each step. For instance, if we try this one more time, 3x times a bunch of stuff plus 1 dx, that bunch of stuff is going to be all this. If we actually fill that in, we'll get 9/5 times x to the 6th, 3x to the 4th, and that's already what we had. So when we integrate, we get the same 3/5 x to the 5th. 3x times x would be 3x squared. Integrating that still leads to x cubed. And then we also have this plus 1 at the end, which is still going to create x. So integrating all this, we still get x, we still get x cubed, we still get 3/5 x to the 5th. What's our one new term here going to be?
X to the 7, 9/35.
Yeah. Or just 30, I guess, because we've got 5 and an extra 6. So 9/30. And then we can keep this going. Do a few more steps, figure out what's being added at each term, and then start looking for patterns. Because you don't want to have to keep integrating this over and over and over and over again. Look for patterns in the newly emerged terms. And those patterns might not hold for the first couple of terms because you get some initial weirdness due to like the plus 1 and stuff like that. But once you've gotten through the weirdness of the first few terms, you should be able to establish a pattern with what comes next. Like for instance, here we've got 3/5 times x to the 5th. What happened to that to turn it into 9/30 times x to the 7th? What changes were made there? Or to put it another way, what do you think the next term is going to be?
It has x to like the 9th.
Yeah, it's definitely going to have an x to the 9. And we can even establish that by the fact that we're taking the previous x to the whatever, multiplying by an extra x, so that increases the exponent by 1, and then integrating, which increases the exponent by 1 again. So anytime you establish a pattern like this, look for reasons why that pattern holds, why it's going up by 2 each time, for instance. And then what would you expect to happen to this fractional coefficient? Maybe focusing on the numerator alone or on the denominator alone.
The numerator should be multiplied by 3.
Yeah, because every time we go through this, we're taking what we had before and multiplying by 3. So that gets an extra times 3. 9 becomes 27. And note that that holds so far. We're going from 1 to 3 to 9. The next step will be 27. And meanwhile, what happens to the denominator in the next step? Wait, should that be 35?
Yeah, I think it should.
Okay, yeah, I missed that. Thank you. I think you had that right in the first place. Because we're dividing by the new exponent, so that should be 35. So what would we be dividing by in the next step?
Should be 9.
Yeah, because if you take x to the 7th times another x, that becomes x to the 9 when you integrate, and we need another divided by 9. So we get 35 times 9. Or if you write it out in factored form, we had 5, we multiplied by 7, now we're multiplying by 9. And then the next step, we'd have presumably an x to the 11, 27 times an extra 3 for 81, divided by presumably 5 times 7 times 9 times 11. So you can establish a pattern here and write it out to as many terms as you need. And in some cases, it may be possible to recognize that as, oh, that's just the Taylor series for cosine of 3x or something like that. Or maybe use some algebraic manipulations to make it look like a recognizable Taylor series. And that's not always possible. I'm not sure I could write out an easy to recognize Taylor series, largely because this is skipping some numbers. 5, skip 6, multiplied by 7, skip 8, multiplied by 9. So it's not just a simple, like, it's not just 3 to the something divided by something factorial. it would require more complicated ways to write that. But even if we can't recognize it as a Taylor series to get the infinitieth term, we can at least write it up to a certain point and stop and say, this is going to be a pretty close approximation. So if you were to type this into a graphing calculator or graphing software on a computer and graph it, you get a curve that isn't exactly the solution, but is pretty close to the solution, at least near the initial conditions. So that's the core idea of Picard's iterative method for approximating solutions of initial value problems. You start with the guess y = 0, because that's a flat line that goes through the initial conditions at least, and then go through this repeated integral method to get closer and closer and closer polynomial approximations. If possible, take the limit as the number of approximations goes to infinity and think of it as a Taylor series to get an exact solution. But even if you can't do that, you can at least get a pretty good approximation. Any other questions on that? All right, then I will see you next time.
Thank you.
Thank you so much.